All right, so we were in the middle of question 11E that says, can we be 95% confident that the CPI and the year are correlated? And I quickly answered that yes. Just to explain that a bit more, we found our correlation coefficient to be 0.9761, and I went to the table and pulled up the critical value for 6 data points, which is 0.811. And since the absolute value of 0.97, this is positive anyway, but technically we take the absolute value of this and we compare it to the critical value, and since this meets and exceeds the critical value, we are in fact can be 95% confident in correlation, positive correlation in this case. Okay. For part F, the model predicts, how does the model predict the CPI in 2016? Well, the predicted value, I'm sorry, the actual value is 240. Let's look at the predicted value. That's going to be the value of the function in year 6. I'm sorry, that's year 5, isn't it? Year 5. $240.776. So we have a slight over prediction because the actual is 240, the predicted is 240.0, the predicted is 240.77, slightly larger, so we over predict a little bit. Part G, use your model to predict the average annual CPI in 2017, rounded to 1 decimal place. So extrapolating here, we're going to evaluate the model. 2017 is 6 years in the future, so that's 243 into 1 decimal place, that would be 0.7, 243.7. Okay. The average annual CPI was actually 245 in 2017, so the model error, that's actual minus predicted, so that's 245 minus the thing that we just found, right? And that's going to be our model error, 1.33. And then our percent error is the model error divided by the actual, which is 245. Oh, you know, I realized I just made a mistake. That was actually supposed to be 245.1. So let me go back and correct that. So that's a minor mistake, but it could throw me off. So let me fix it. And I'm going to have to redo my computation. So it's 1.43. Sorry about that. And then now our percent error is that model error divided by the actual, which is 245.1 times 100. And so it is 0.58%. Okay. Part J, according to this model, what's the first year in which average annual CPI will be greater than or equal to 250? So I'm just going to use the table for this. Now I do need to input 250 into my equation editor as y2. And then let's go to the table, and actually need to, let's reset the table starting at time 0. And now let's go to the table. Now we're looking to exceed 250. And that happens in year 9. And this would be a case too where we would be using the integer or the discrete domain, integer domain. So we're always going to just round up. So if you did this using Calc Intersect, you would still end up rounding up to year 9. The nice thing about doing it with the table is that we don't have to bother with rounding. I can just immediately pick 9. And so 9 years after 2011, so that's going to be 2020. All right, let's look at number 12. An investment account has a doubling time of 20 years. If $5,000 is invested in the account, what will be the balance after 10 years? So we're going to have to get the model before we can find the balance. Now, in order to write the model, what we are given is an initial amount and a doubling time. So this is sort of analogous to the half-life situation. We're not given a rate, we're given a doubling time. So this is like being given the half-life, and if you recall what I said there, if you are given the half-life, you basically are going to do exponential regression. So I'm going to do exponential regression here as well. Actually, let me do this on the whiteboard where I have a little more room to work. And my points are going to be times 0. I have $5,000, and after 20 years, I have double that, so I have $10,000. That's just what the problem tells me. So those are my 2 points, and I'll do exponential regression with that. Let me clear my lists. Okay, and then we'll do exponential regression. And there's our model. And so to find the balance in the account after 10 years, now that we've got the model, we just need to evaluate it with an input of 10. And we get $7,071.07, rounding up. And that's all we have to do for question 12. All right, let's move on to 13. Consider the exponential function a of t equals 235 times 612 divided by 235 raised to the t over 4. And we have a bunch of questions about this. Now, I hope you recognize what you're looking at here is a exponential function passing through 2 points, and the 2 points that we are passing through are given. As I was saying, this is passing through 2 points, and what 2? Now, you don't actually have to do this, but just to show you what I'm looking at, I'm looking at the exponential function that passes through these points. That's the first one, and then the second one would be, okay, so if I do exponential regression on these 2 points, I will get the same model. It will look a little bit different, but it will be the same model. But we don't have to. We already have a perfectly good form for this, so we don't have to do exponential regression here, but we do have to enter the function into the calculator correctly. So let's type it in. I'm going to use a lot of parentheses here. Parentheses around my exponent, of course. That's very important, and I believe that's got it. So there's our model. So if we want to evaluate the model after 4 years, or I guess we don't know if it's years. we don't know what the unit is here, but so we're just going to evaluate y1 of 4, and so that would be 612. Now that shouldn't actually have been a surprise, right? Because if you look over here, notice that I actually computed that already just by looking at the function. So, you know, if you're paying attention, you don't really have to compute anything here. I guess I wasn't paying attention because I did compute it, but in any case, there's our answer. What about part B? Solve the equation a of t equals 1,000. So for that one, I can use calc intersect. Trying to anyway. Because that's essentially what this is saying, is when do these two intersect one another? Let's go to the table and see when it happens. And it happens pretty quickly, between 6 and 7. So I can probably just do 10 for my window and then do zoom fit with that. And there's our intersection. And it is 6.05. Okay, what about the average rate of change on these given intervals? So this is definitely something that I would do in the stat editor. And I have to first enter these are all x values, right? So 0 to 0 up to 10. So let's enter all these x values, 0, 2, 4, 6, 8, 10. And then my second column is going to be y1 of L1. And so that's the function evaluated at all those inputs. And now for column 3, we can do delta list. L2. Oops, I'm sorry, I just messed that up. In the header. Divided by delta list L1. And there are the average rates of change that are requested. So we would then copy all those down and enter them in. All right, let's go into part D. Find the growth rate as a percent. So this one's a little bit more tedious because we can't immediately read the growth rate off of this. We have to kind of do a little algebraic finagling here to get it. But what the growth rate is it's this. It's 612 divided by 235 raised to a power. But what power is it? It is raised to the 1/4 power. There's no variable there. Pay attention to that. There is no variable. That's my factor. That's my growth factor. And then to get the growth rate, I subtract 1 from this and then put it in percent form. I multiply by 100, so we have 27.03%. Okay. One last question. Find the daily decay rate for a radioactive material that has a half-life of 37.22 days. I'm running a bit short of time in this last question, so I did a bunch of work off camera. But here's the idea. We are given a half-life, and so this is actually point data. So my point data would be at times 0. I'm going to just say that I have 1 unit since I'm not given a unit. And then after 37.22 days, I'm down to a half. So this is my point data. So I enter this in the calculator and do exponential regression. That's what you see right here. And so this is the result of my exponential regression function. To find the decay rate, I'm going to first find the growth rate, which is b minus 1. Then I'll change the sign